Here we are in part B, where we will continue talking about entropy. In particular, we will go down into the microstates, so we can see how this can be measured at the molecular level. So what we're going to be talking now is, you already know what spontaneous is. We're going to talk about reversible and irreversible process, and also how they happen when the temperature is kept constant or isothermal. We are going to see, like I mentioned, how we can relate entropy of the system into the different microstates or all different possibilities of the system. And we're going to see how entropy is also affected by the molecular motion of different type of structures. Once we do that, we're going to see how we can calculate the entropy change on the surroundings when the temperature is constant. And we're going to see how we can predict the sign of the delta S for physical or chemical process, which we already did a little bit when I was talking about gases are moving faster and so on, in compared to the solids or the liquids. So let's begin by defining reversible and irreversible process. So a reversible process is a process where, by simple changes, it's an equilibrium process actually. By small changes on the system, you can make the reaction spontaneous forward or spontaneous backward. Irreversible process would be a process that when it happens, there's no way to get back to it. So, on more technical words, the reversible process, the system changes so that the system and surroundings can be returned to the original states. So it's basically Le Chatelier's. You affect the equilibrium, it changes to get back to the original state. And an example here is heat. If the system is releasing heat, the surrounding goes up. And if it continues going up, eventually the system will be colder and the heat will go back to it. So that's a system that is reversible pending the conditions. An irreversible system would be something like this. If you have a gas pressurized and you expand the volume or release the pressure by removing that wall, moving the wall up, the gas will expand and take as much space as it can take. It will not go back into what it used to be before unless you force it to be. So that if you have to force it, it's not spontaneous. So a reversible system is a system that once it attains a new change, like a gas expanded into a bigger space, it doesn't go back to the small space on its own. That would be a irreversible system. Based on our reality, that doesn't happen. So let's continue talking about entropy, and then we're going to relate entropy to being spontaneous or not. So once more, entropy is a measurement of the randomness or the disorder of a system. We said that entropy, the same as enthalpy, is a state function. Because as long as you know the final state and the initial state, the difference gives you the entropy. It doesn't matter which way we go, we know the final state and the initial state. We can measure the entropy of the surrounding, or the change in entropy of the surrounding, by measuring the heat that is released by the system. So if this is my system, everything else around it all the way to infinity is what we call the surrounding. All together is what we call the universe. So if the system is releasing heat, the particles on the surrounding are going to start moving faster now, and that's going to increase the disorder. They're gonna be free to go everywhere else. They're gonna be moving faster because the system is releasing heat. So when the system releases heat, the surrounding acquires that energy and the entropy increases. So by knowing how much energy the system is releasing and knowing the temperature at which this process is happening, that gives us a measurement of the entropy. So by measuring the heat of the system, you can find the entropy of the surrounding. So the one gives to the other. And that's happening at constant temperature or isothermal process. So remember that formula. If you know how much the heat the system is releasing, you divide that by the temperature at which is happening, and that gives you the change in entropy of the surrounding, not the system. And if we put together everything we know, so I just told you that if you measure the heat that is released at a given temperature, that gives you the change in entropy. We said before that if you're measuring heat at a constant pressure, that's the same as enthalpy. So if you're measuring the heat of the system, you just got the enthalpy of the system. So we can modify this formula to show you that the change in enthalpy of the surrounding is nothing more than the enthalpy or energy of the system release divided by the temperature at constant temperature. And we can even go further. Since the system that we're looking at is a chemical reaction, as long as we're talking about that chemical reaction, that's the system. So you can say that this is the enthalpy of the reaction divided by the temperature give you the entropy of the surrounding. So the three formulas are telling us exactly the same. They're just doing it with different symbols, relating heat and enthalpy of the system to enthalpy of the reaction. So going back to the second law of thermodynamics, the entropy of the universe increases in any spontaneous process. So if the system is spontaneous, then the entropy is increasing. So you can see it like this. If the system is reversible, then the change in entropy is on equilibrium. So the changes in entropy of the system plus the change in entropy of the surrounding had to be zero for the system to be reversible or in equilibrium. For an irreversible process, the delta S of the universe had to be bigger than zero, because the entropy is not going to return, it's not going to be reduced on its own. So entropy, always based on the second law of thermodynamics, entropy of the universe increases in any spontaneous process. So if it's decreasing, it's a non-spontaneous process. And decreasing means that it's getting better, more organized. Nature doesn't want to be organized. That requires energy, so you're going to have to apply energy, which makes it non-spontaneous because you have to do something to it. So remember those 2 points. The change in enthalpy of the universe has to be equal to zero to be a reversible process. It has to be bigger than zero to be a spontaneous process, or irreversible process. All these two are happening on a spontaneous process. So let's look at entropy at the molecular scale, which is basically what I showed you with the fish, But now it's not an analogy anymore. Now it's the real thing. So we're talking about two atoms, and the example that is giving us is if I have two atoms on two chambers separated by a valve. If I open the valve, making the volume twice as much, those two atoms will immediately distribute themselves. And in this particular situation, with only two atoms, you're going to have four possible arrangements. And we're going to call this microstate 1, microstate 2, microstate 3, microstate 4. So based on probability only, you're going to have four different situations. Each one of them is what we call a microstate. So Boltzmann, which as a scientist, described entropy in terms of the molecular level this way. And the most probable, as you can see, is going to be the one that gives you one molecule on each chamber. The color change, but the probability of 1 and 1 is twice as much as the other two combined. So does it make sense then that if I had more particles, I would have to have more microstates? So we can see how the number of particles creates a lot of different variations. So what we're talking about in this chapter, thermodynamics, that's what we see when we look at all millions and millions and trillions of molecules all together. So something we can actually see. At the statistical thermodynamics is what relates to this, what we're talking about, to the microstates. And it's based on statistical probability. So once more, each one of those possible situations, that's what we call a microstate. And it's based on the position of the molecules or atoms and their kinetic energy at that particular time. All this can be summarized with this formula that measures, remember that so far we have been talking about the change in entropy. This formula allows you to measure entropy on its own, not the change, but this is how you will measure the initial and final. On the bulk or things that we can see with our eyes, we only measure the change by observing the change. So we're not going to go too deep into this formula. Just be aware that there's a formula that allows you to measure entropy at the molecular level. And it uses the Boltzmann constant. So you probably see this on Alex. We're not going to talk much about in the lecture. And this is another variation. If we're talking then about remember, this formula gives you the entropy on its own. But if we're talking about the change in entropy, then it's nothing more than the final entropy on its own minus the initial entropy on its own, which you can summarize this way. So we can see right away how increasing, where W represents the number of microstates, by increasing the number of microstates on the formula, it will give you a bigger number or a higher entropy, changing entropy. So still thinking about the molecular level, how would volume and temperature affect the entropy? We know entropy is the probability, at the molecular level, entropy is the statistical probability of different microstates. So if we increase the volume, so if we have something like this with 3 particles, right? The most probable would probably be a distribution like this. as far away as possible from each other, and so on. But if we increase the volume, now the probabilities can be so many different. It could be like that. It could be like this. So this is going to have a lot more microstates by increasing the volume, so therefore increases the entropy. What about increasing the temperature? Where increasing the temperature is going to allow the molecules to move faster. So you're going to see them, if you were taking a picture every nanosecond, you will always see a different picture because they will be moving so fast that you will rarely catch them on the same place. So increasing the temperature because of the increase on kinetic energy also increases the entropy. So be aware of all those things when you're trying to visualize the entropy of a system. What about the molecules on their own? So we have water in here, and you know from general chemistry 1 that water is going to have a bent shape. But you can do this on a ball and stick model, and it's going to be very rigid. In reality, they're not rigid. In reality, this bond can be going up and down, so it could be like a scissor. The bond can be stretching in and out, and it can do that simultaneously with the other one, or while this bond is stretching out, this bond can be stretching in. So every one of those possibilities are new microstates. So the more possibility of different motions on the molecule, the higher the entropy. And here we can see the stretching in and out. We can see the scissoring motion. This is the not coordinated in and out. And the molecule can rotate on its axis. It can also, I imagine, it can also rotate like that. So there's a lot of different information versus if we have carbon monoxide, for example. The only thing carbon monoxide can do is stretch in, stretch out, or I don't know if you can say that it can stretch in and out at the same time. But you can see that there's a lot more different motions in the water. So knowing the Lewis structure and knowing the molecular shape can give you an indication of the entropy of the system also. In summary, the entropy is going to be affected by changes in temperature that are going to change the kinetic energy of the molecules, therefore the randomness. It's going to increase also when you change the volume where the system is taking place, because now you can find the particles in several new different places, increasing the microstates. And the actual molecule by itself can be having movement that increases the entropy of the system also. So all this is very important to visualize when we're trying to understand the overall entropy of the system under study. Physical state, you already know that. So on a solid, the molecules are going to be set up on a fixed lattice. So they're very organized. So very organized means low entropy, right? Because entropy is disorder. When you go into the liquid, now the molecules can move more freely, so the microstates are going to increase the possibilities of finding the molecules on different places, and even more when you make it to the gas. Therefore, the entropy of a gas system is always higher than the entropy of a liquid system, and is higher than the entropy of a solid system, because the possibility of different microstates increases with increase in kinetic energy. Also, you have a chemical reaction going on, like the one we saw at the beginning on part A, if the reaction starts with one molecule and it gives you two molecules, now you increases the possibility of more microstates, so that increases the entropy also. And every time the entropy increases, we say that it have a positive symbol or positive sign. So let's see how we can use all that now to talk about this. For each pair of substances, choose the one that you expect to have the higher standard molar entropy. And we're going to represent a standard with that symbol, which means it's at 25 degrees Celsius, 1 atmosphere of pressure, and if it happens to be a solution, 1 molar. So on this case, the molecule is the same, so we don't have to be worrying about different movements. The only thing that changes is the state. It's going from solid to aqueous. Aqueous means that it got dissolved, so it went from 1 particle to 2 particles because it's aqueous now, right? And in addition, there's water on the system now. So you got a lot more disorder. So definitely the entropy is increasing. It's going to be bigger than 0. What about the next one? The next one, both of them are gases, so we cannot say that it's going to be based on the state. However, this is methane, this is ethane. Methane is just like this. So each one of those bonds can be doing different movements. Meanwhile, ethane is like that. So now you have more bonds because you have more atoms, right? So the possibility of different movements increases also. So as you increase the number of atoms on a molecule, that creates more possibility of movement, therefore higher entropy. So the entropy on this one is also increasing. So with that said, go ahead and do that. Make sure you explain your reasoning, just like I did. So let's do another problem. Without doing any calculations, so no calculations required, determine the sign of the system. Remember, we learned this, right? We learned delta S of the surrounding equals minus Q over T, which is the same as minus delta H over T. So that's not what we're looking for here. We're looking for the system. However, after we do find the delta S of the system, we are asked also to find the delta S of the surrounding, so that's where we're going to use this formula. And then we also have to predict under what temperatures, if any, the reaction is spontaneous. What do we know about spontaneous? Delta S of the universe equals 0, or delta S of the universe is bigger than 0. This would be the reversible, and this would be the irreversible. But both of them are spontaneous systems. So 0 or bigger than 0 to be spontaneous. So let's see how we do this then. So what do we know? The delta S of the system, we find it by using these factors. Liquid versus solid, solid versus gas, increase in number of molecules, increase of number of atoms, and so on. So that's how we know the symbol, the sign for the entropy of the system. So what do we have? We have 3 molecules are producing only 2 molecules. So delta S of the system is going to be less than 0. It's becoming more organized. More organized means entropy of the system is less than 0. The entropy of the surrounding is going to be equal to the minus delta H over the T. And the problem doesn't give us any temperature, right? But what do we know? We know that the delta S of the universe is going to be equals to delta S of the system, which is negative, plus delta S of the surrounding, which is positive. This temperature is Kelvin, so it will never be negative. Kelvin is always a positive scale, from 0 to infinity. So Kelvin is always a positive scale. Negative, negative, that gives me positive. And I know this is divided by T. So for this to be spontaneous, this has to be bigger or equal to 0. That's what spontaneous means, right? So delta S of the universe has to be bigger or equal to 0, and it's going to be a combination of the delta S of the system plus the delta S of the surrounding, which means that this temperature has to be a big number. On the contrary, this temperature has to be as small as possible so that this positive becomes bigger than the negative, therefore guaranteeing that it's going to be bigger or equal to 0. So to be spontaneous, it has to be the change of the entropy of the universe has to be bigger or equal to 0. We know that the entropy of the system on this case is negative, and the entropy of the surrounding is positive. Since we're dividing by the temperature, we want the positive to be the biggest it can be. So when you add it to the negative, it will give you positive. So that's how we approach this problem. So with that said, go ahead and work on those two reactions and decide the symbol for the delta S of the system, delta S of the surrounding, and then decide the type of temperature you need to guarantee that the delta S of the universe is going to be bigger or equal to 0, therefore spontaneous. And with that said, you know what a spontaneous system is. Now you understand better the reversible and irreversible process, and you know how to relate that to entropy. We saw how the entropy relates to the different numbers of microstates. And you saw that entropy can be measured by K, ln, W, where W is the Boltzmann constant. In addition to that, you saw how temperature, volume, and the actual shape of the molecule can affect the entropy of the system. We saw the formulas on how to calculate the entropy of the surrounding using heat or enthalpy divided by the temperature at isothermal, so the same temperature. And we saw how to, by looking at the reaction or by looking at the state, liquid, solid, or gas, we saw how we can predict if the entropy is increasing or decreasing. And with that said, we can close part B of this presentation. So when you come back, we're going to be doing some more calculations, and we're going to start talking about the Gibbs free energy. So that's it for right now. Talk to you soon. Take care.